Hi, how is everyone?
Hi,
Good.
Farhan. Good.
Is there a distortion in the audio?
Not for me. It's good.
All right, because I am hearing a little bit of an echo from your side. Okay.
Farhan, do you have a new link for today as well for collab?
Uh, there is a link. Yes, I'm going to share that. Uh, I have just deleted some of the code to make it like to do a little bit of cleanup. Uh, there are no additions, but let me. Yep. I just shared the link in the chat box. I'm waiting for others to join because this is a really important session. Uh, but we have only 10 participants so far. I think I need to ping everyone in Slack. Yep, I'm still gonna wait for another couple of minutes. I think we'll start at 10:05. But the link is in the chat box, so make sure you have that code running open in Collab. Should be W3S2.
Farhan, is it updated? Because at the last cell, I see that it's sort of incomplete. Or is it, will it be filled later today?
It is updated because I think the last cell has a to do, and oh no, hang on.
It just
I think
says
this is a
try
new.
the,
Yeah, yeah, yeah.
okay,
I think I didn't save the notebook and I committed it. And I'm sorry about
okay.
that. Give me a second. Okay. Uh, so sorry about that. I updated the changes, and I'm just verifying that it's correctly reflecting on GitHub.
Not sure if I'm doing right, but I still get the same.
Yeah, that's what I'm trying to check. It's updated. Did you try to pull it right now?
Let me do it one more time.
Let me also try because I don't have the code open so far. For me, I am getting the latest version. Are you
So after
still
the constant alpha, there is this try SARSA and Q-learning with the link. Is that
right?
the
There is
last
only
cell?
one link. Yeah, right.
Okay,
There's just
yeah, then I see it.
because there's no starter code for today. Uh,
Okay.
because we sort of want to implement things
Fran, I
from
think
the
you're muted.
God. How did I mute myself?
No, we can hear you.
I'm not muted actually, but
Farhan, I can hear you.
Yeah, I
I
can hear
think there
Farhan.
is some audio issue because there was another session and I was facing some problems there. I have reported it to Zoom. Let's see if they can fix it.
Farhan, could you share your screen?
Yeah, I'm gonna do that in a second. Can you see the screen now?
Yeah, if you go to the last section, how does it look like?
Yep. It is just one extra cell which says how can we get faster convergence.
Uh,
Yeah, I don't see that yet as well.
That is weird. I think everything that can go wrong is going wrong. Uh, I just
Um,
trying to get it here. It's reflecting right now. Maybe give it another try. I just opened the link.
I had to close the Google Colab and then reopen it, and then I was able to get it to update. And I actually did it like
Okay.
3 or 4
Okay.
times. I don't know.
oh, that's what I'm
Yeah,
doing
yeah.
actually.
That could be caching something somewhere.
Yeah.
That is weird, but so I think we can get started. Like, try to get the code,
Yeah, now it's fine.
and it's not a lot of stuff. Like I can also share that link, but essentially the rest of the code is same. I just removed the intermediate steps where we were trying out stuff that wasn't really working, but we were doing it for the because we wanted to understand things. So again, I'll do save a copy and drive because it's a lot of work. I don't want to lose it. And then we can start running the cells. So So basically what we are going to do today is we are going to look at two specific algorithms, which is what everyone gets introduced to when they are learning reinforcement learning. And they are very closely related to the algorithm that we have implemented so far. So the reason we don't have any starter code is because we sort of already have a reference code, which is what we implemented yesterday. But we will have to look at the algorithm. We will have to make sure we understand what the algorithm is saying and how it is different from the approach that we followed yesterday. But it's not a lot of difference, not a big difference. So the general idea is same, but a few things changes. So just run through all the cells, make sure you have all the variables updated. There is one small change that I have made. So there were two sort of competing approaches. The first one was just epsilon decay, where we were still using the idea of visit count and dividing by visit count to normalize things. And then there was the alternative approach where we were using constant alpha. So we did away with the denominator and we introduced a multiplier which was constant through all the iterations. And people pointed out different sort of optimizations or different starting values, different combination of the hyperparameters. Like if you use an alpha value of 0.001, that outperforms a value of if it's 0.1, yeah, 0.01. So the only difference in terms of code is that the iterations here I have set them to 5,000, and when you do that, so this is still the only epsilon decay approach, right? There is no constant alpha here. We are still using the visit count table, but if you set the iterations to 5,000, I think we get the right optimal policy, right? You can see for every cell you're getting the right policy. You can try this a few times to ensure that you always get the correct results. With constant alpha, right? With constant alpha, it seems that it is still not getting, in this case, the optimal policy for this cell and this cell. But let me check. Yeah, so the alpha, when alpha is set to 0.001 and number of episodes is 5,000, looks like we are still stuck somewhere. We are not able to update a few cells. But sometimes you do get, sometimes you will get just the right policy, the optimal one. So let's try. Yep. So even now, these two cells seem to be stuck somewhere, and this wasn't happening when we tried. I think if you try something like 10,000, it will take a little bit extra time, maybe 40 seconds or so.
Hey, I have a quick question.
Yeah.
So, instead of using epsilon, can we use the probability based on the return table?
How would you do that?
So in the return table, it tells you the returns for each direction, right?
Right.
Maybe some are, and
Okay.
then yeah, and based on that, like you give different probability based on
Yeah.
the
So
return.
yes, so that is actually used. We haven't used it. Yes, you used it yet. Um we can use it. We can see how well that performs in this case. But the two algorithms that I was talking about, which is SARSA and Q learning, when you apply those algorithms, in fact, when you apply SARSA to a situation where you have non-deterministic actions, these actions are stochastic, and there is a probability distribution. So there's something called expected SARSA, which is basically what you are saying. So instead of assuming, although it's not exactly what we are discussing, but the idea is same, that because there are different uh, different returns, so why don't we use them as expectation values? Why don't we use them as probabilities and then take some sort of an average over them?
I see. Thank you.
Sure. So now, even now, I'm not sure what is going on. Probably this might have to be debugged.
Actually, in the first go, I was able to get a solution which
Then,
got me to the goal.
right. So even in this case, like, it's bringing me to goal, and it is a short, like, it is one of the shortest paths. That is fine. But over here, this one, this cell, and this one, they don't have the right policy, because they should, this one should ideally point downwards and this should point right, which is what you get without using constant alpha. So here you're getting the right policy. So something is amiss. I'm not quite sure. There could be a bug somewhere. Okay, and I won't spend a lot of time. I'll debug it later on. But what we want to do today is we are like using 10,000 steps or so, or in this case 5,000 steps or so.
Farhan, just a comment.
Yeah, sure.
So if you scroll down, right, your policy, you say that you don't like those two arrows in the policy because they should point downwards. But based on our rewards structure, which gives 0 penalty for moving to an unmarked position, I think that gets reflected in that arrow, right? There is.
But we still are using the idea of a discounted return, right? So if you take a longer route, you will still get a less reward.
I see. Good point. Okay, thank you.
That was the reason that we thought of discounts in the beginning.
So for this problem, Farhan, does it mean that the Monte Carlo method is better than using discounted return?
So there were actually two reasons why we settled for a discounted returns. One was, of course, this reason that we want to take the shortest path. But the real reason was that I mentioned that very often you won't know what the reward should be for an action, right? And in those scenarios, you just have to settle for a reward of 0. And that means that you have to ensure that even if the reward is 0 most of the time, and only in certain maybe terminal states you get a penalty or a reward, you still penalize the agent if it doesn't take the most efficient route. Does that answer you?
Because just the one previous one is doing better in terms of the result, I'm just wondering if that approach is better in this kind of problem.
That is right. In this case, the previous one is doing better. In fact, I think someone suggested that even if you, what was the suggestion? There was a change over here, right? And I think they were just not dividing by visit count. So if you just stop normalizing at all and just use this code, it still was outperforming this code over here. But one thing we have to keep in mind is that this is one specific example. And in general, you want to use this approach because when your visit count is really large, like if you are iterating millions of times, which will happen even in smaller settings, then probably the outcomes will be different. So right now, because we are dealing with a very small problem, maybe that is one reason why the behavior is not always consistent. But I do remember that, if you set it to 0.01 and set this to even 5,000, then I think we were getting at least a better policy. Yep. So when you set this, it is still not perfect because this cell over here, this is still misbehaving, but the rest of the policy is optimal, right? So we have to be careful with the hyperparameters. 0.01 seems to converge faster. Even if you reduce the number of episodes to like 3000, it was working, but you're not always getting the correct results. And this is something which I was mentioning yesterday, that when you're trying to achieve certain results in reinforcement learning, very often you will have to look at a window of results. So don't look at one execution and decide that this policy is good or not, because there might be a lot of variation. So you have to see how much variation is there and then smooth that out, and then see how much reward, how much return you are able to get consistently.
I had a question.
Yeah.
In the collect epsilon greedy episode from returns table, why is there a multiplication by epsilon? Sorry, by the number of actions when calculating the probabilities? Like, I would think that would make it not add up to 1.
Right.
Yeah. So line 11. Why is there a multiplication by len of actions?
Length of actions multiplication is there because we want to scale that particular list from size of 1 to size of 4.
Right. So this is a Python feature. So if you look at this is a list with just one element, and the value of that element will be epsilon by 4 because length actions is 4, right? And if you multiply, so this is not actually multiplication, this is a little bit of confusing Python syntax. But if you have a list and then you multiply that list by a number, so Python just creates another version of the list which is 4 times as long. So this is just a shortcut for repeating this 4 times.
Okay. I've never written syntax like that. I would have done like n times np. So times len of actions is like times np dot ones
Right.
of size action.
Yeah, it's not np dot ones because then you have to multiply it by epsilon, right? Epsilon by length action. Like you want every entry to be epsilon by 4, so you can initialize with np dot ones and then multiply by epsilon by 4.
Okay. So it's just some special syntax that operates on lists.
Right.
Okay.
So going back here, this is still not perfect. I will have to debug this, which is going to take time. But what we will do in the meanwhile, like the focus today is trying to see how we can achieve faster convergence, right? So we don't have any starter code today. I want everyone to do a little bit of reading. We will discuss because it tends to be a little cryptic. Like it's not very easy to understand how that algorithm that we're going to read about maps to what we have implemented right now. But first of all, there is a link here, and that will bring you here. It's a long page, but I just want to focus on these 2 algorithms. One is SARSA and Q-learning. One says it's on policy, the other says it's off policy. We will discuss that as well. But I want everyone to spend like 5 minutes, read it very carefully, and see how this is differing from the last implementation, basically the last algorithm we're looking at.
So Farhan, in terms of the policy difference between SARSA and the Q-learning, it's just that for Q-learning, you're trying a different policy on the next move to get the different like off policy rather than just following the policy that you have for SARSA, right?
Yeah, that is a subtle difference. Actually, it's a big confusing point for many. I was also confused for a long time between SARSA and Q learning, and we will come to that thing, like what is the difference between SARSA and Q learning. But what is the difference between either of these algorithms and what we have implemented in our code?
Farhan, did you share a link to this article?
Yes, it is in the last cell, right? Uh, Over here. Sorry. Uh,
Oh,
could you
okay.
see
Thank you.
that?
Yeah, thank you.
So in this algorithm, is the Q value supposed to be the return?
Yes, yeah.
Okay.
Q is basically the returns table. We haven't used that notation,
Oh,
but
okay.
it is generally called action value and represented by Q.
Okay. Sorry, I haven't really read the literature of reinforcement
No,
learning.
that is fine because we haven't really done a deep dive into the notation and the terminology. We are supposed to do that in this session and the next one.
Okay, thank you.
There is
Farhan,
one, yeah.
Sorry, the only difference is how we update the return the Q value function, right? Or am I missing something?
There are actually a few differences, but there is one major difference which I want everyone to be able to spot. But you are right that there is a difference in the way we are updating the table. And can you spot what that difference is?
So I think the difference is that in SARSA, the first term within alpha,
Mhm.
and so in our algorithm we use QSTAT directly check the difference.
Right.
But sorry, a Q ST plus one, AT plus one.
Yep, that
I mean,
is right.
we're using the previous QSTAT, but
Yeah,
here it's
if you
following the path that it's picking.
right. So I want to sort of let me see if I can paste it here. I don't know if this
Yeah, I
was
think
enough.
I think one thing that would help me, I don't know if other people are also confused, is to understand what all these different letters are. Like what are V, G,
Yeah,
R, and Q? Because I'm still confused about that.
right. Uh, so yep, let's talk a little bit about the notation first. So Q is basically your action table, your returns table, right? Q is that table, and obviously S and A denote the state and action. Uh, R over here is the reward, right? So if you're going from state T to state T plus one, RT plus one, they're calling it RT plus one. I think it makes more sense to call it RT, but this is basically the immediate reward, not the return, not the discounted return, the immediate reward that you get from when you go from state T to state T plus one. What else is there? We aren't using V anywhere in this formulation. but there is, yep, I think that's all we need to explain, right?
There's a V and there's a G
Uh,
in the value estimation. So I guess V you said is the return, right? What is G?
can you point me where V and G? I know V and G are part of standard notation, but are they being used in these two paras?
Oh, I was looking above SARSA because it was saying that
Okay.
SARSA is a
Okay.
type of TD learning.
Okay.
So I was looking
Okay.
above that to understand TD learning.
Yeah. So yeah. So V is basically what we use for the policy. So V is actually called the value function, and V is the sequence of actions, the best action, state action pairs that we picked when we wanted to print the policy. So if you go here and look at, yep. Okay, in this code we aren't really printing it, but V is basically called the value function, and you can think of it as the list that tells you what is the highest return in each state. So the difference between V and Q is obviously the rewards table, the returns table, and Q tells you the maximum return that you can get for each state and action pair. What V, instead of being a two-dimensional table, V is more like a list. So V just picks the best action and the corresponding return. So if, for example, if we look at, sorry,
So it's like the taking the greedy policy.
yeah, it's like exactly taking the greedy policy. So if I start with this state, then obviously this is the highest return because this is positive. So when I try to compute V, I'll pick up this value, and then this value will take me down, which will take me to state 4. In state 4, I think this is the highest one, so I'll pick this value. So in the end, I will have the highest value corresponding to a policy, and that is sort of
Okay, so Q is sort of a function of two variables, state and action, whereas V is the same information basically, but it's only a function of state and giving you the max.
Correct, absolutely.
Okay.
And G is just being used for returns.
Returns or rewards?
G is returns, R is reward.
Okay, so that's what we called RET.
Oh, sorry, go ahead.
I was just saying, so that's what we called RET. It was sort of the instantaneous return. Okay.
Yeah, GT is the instantaneous return at time step T for a specific state and action pair.
Yeah, I think there's a description of what these terms are near the beginning of this article.
Yeah.
And
So
the
actually,
G,
this is, the whole article is sort of there in the reference section, and I want us to go through the entirety thing. But I just wanted to, I was thinking that we'll do the terminology first, and then we will try to go through the entire thing. But it's fine. Like if this makes sense, then let us just try to understand the notation. So V is your value function, which is a function of just the state. So you give it any state, and it will tell you what is the highest return in that state. It doesn't care about action. It will just take the maximum return that you can get across all 4 actions. Q is your returns table. We have been using it all the time, so we understand it. G is representing the immediate reward. What else is there? Yeah, I think that is all the notation we need.
isn't R the immediate reward and G is the accumulated discounted return? I think that's at least what's described in the.
G is the accumulated discounted return, and R is the immediate reward.
Right. And the main difference between SARSA and Q learning seems to be how the best action is chosen.
Right. But what is the main difference between either of these algorithms and the one that we have coded up?
You're updating the queue in the middle of the episode.
Yep.
So every step you're updating queue, your table.
Right. So because this isn't really looking like pseudocode, so it's a little hard to tell. But if you look at the update equation over here, right, this one, so and then look at the equation that we are using. Over here, So the only difference is that we have used this shortcut notation plus equal to. If I get rid of that, sorry, if I write it in the expanded form, then obviously this is my queue, the returns table. So this matches with this equation, right? This is your queue of ST and AT, and then you have alpha times something, which we also have alpha times something. But here you have got return and then minus the current estimate. And if you look at this, so it also, the second part is the same, the second term is the same, but the first term is different. The first term is the immediate reward plus this discount factor times the whatever value is there in ST plus 1 and AT plus 1. And over here in our code, it was the return computed from the current state. So we were in state S and action A. So we went all the way from SA to the next state, next action, next state, next action, until we hit terminal state, and then we computed the return. And so the difference basically is that if you want to compute returns, which we were doing in this code over here, then you have to simulate an entire episode and then update this table, right? That is what we were doing. We were calling this function, we were calling this function, and then we generated an entire episode, and then for every state action pair, uh, we updated the table. But what is really happening here is that you want to speed up things. So if you think about it intuitively, so why wait for an entire episode to get generated? Every step is giving you some information, right? So every time you make a transition, you're getting some additional information. So why not update the policy immediately? Now what happens is, if you want to update the policy immediately, then obviously you cannot compute the return, because to compute the return you need to generate an entire episode, and that is why you have to approximate the expected return with something else, right? So what this algorithm does is, it only executes one step in the episode, and from that one step you will get the reward, right? This part. uh, and then we know that because of the recursive relationship, if you know the reward and if you know the next state, which is ST plus 1, then you can sort of get the return, right? So this is the equation that we were using in the dynamic programming approach, right? So if I want to find out the return for state ST action AT, then I will look one step ahead. I will look at what the reward is corresponding to the transition from ST to ST plus 1, that is RT plus 1, and then I will look at what is the maximum reward for the next state, which is ST plus 1 and AT plus 1. So we may have to go back and look at the dynamic programming implementation if you want to do that, but I just want to make sure that everyone understands why this could be used in place of an actual return. Of course, if you were to simulate the entire episode, perhaps you will get a better estimate, because that was an actual episode. But the good thing about this update is that after every step you are improving the policy, right? And then you expect that if you are doing that, then you will perhaps converge faster than the approach where you run an entire episode, then you update the policy, then you run an entire episode. Because there, when you are generating an episode, you're generating the entire episode from the same policy. In this case, when you generate, you are still generating episode, but every step in the episode, that is likely to come from a new policy, because you're updating the policy, you're updating the returns table after each step. Is this making sense to everyone?
It is. Does it also mean that we can start from an intermediate state instead of starting always from the initial state?
So right now, with the setup that we have, right, we don't want to modify the environment. So because the top loop is still iterating over episodes, so you would like to reset the reset the environment there, and then always start in S0, which is your starting state, which is the top left.
So in terms of the work that we've done up to now, we never did any TD learning because everything was a full episode, right?
Right, we never did TD learning. And TD learning, because it's needed for two reasons. One, of course, it will generally converge faster than the approach that we were using. And of course, there will be situations where there is no sort of so which are not what they call episodic tasks, right? So where there is no natural end of the task, like in many situations, if
But it
there's
doesn't
a
require terminal state.
right. So you never reach a terminal state.
So in terms of another difference, where it says that it's always applying the epsilon greedy, but for us, we're also doing some probability to explore as well, right? So isn't that another difference between the two?
So this is the exploration part, right? When you apply the epsilon greedy policy. So this is exactly what we were doing. The only difference is that we were generating the whole episode, but this is doing one step at a time. Right. So it's applying the same. The approach is epsilon greedy, which means when you're going to pick this A, so this should ideally say argmax greedy or something like that, which is not spelled out because there are different ways of doing this. So because it says epsilon greedy is commonly applied, so it's not always epsilon greedy, but we are going to use epsilon greedy. So every time you pick that action, you again use the same 4 different probabilities and you pick them according to probability. So there is still a small chance that you'll pick a random action, which means you are doing something in between exploration and exploitation.
I see. So is epsilon greedy the only known method for exploration and exploitation kind of problem right now?
Yeah. But so if you want to explore and exploit both, but you are free to use just the greedy approach here if you want to sort of experiment with this. So instead of using epsilon greedy, you can just use the pure greedy, or you can use some other variant that you can think of.
I see. Okay.
But if you
Thank
want to blend the two, then epsilon greedy is the way.
Farhan, I have one question. So let's say we are only doing the pure greedy approach. Then do we still try different policies? Like the policies would change within one experiment? Because you said like in the previous case, we just follow one full episode. But in the SARSA method, we might actually do different policies within one experiment, right?
That is right.
I'm trying to understand how that will happen, because if say we are taking a pure greedy approach, then based on the Q value function, it's always looking into the future, right? It's always taking the max of the future.
Right.
So then I'm thinking that the episode would just follow the same.
No, the reason that won't happen is because right after you do that, you update this thing, right? You update this entry in the table.
Right.
In case you happen to be in this state, right? Whatever your ST and AT is, in case you happen to be there, then obviously you will get a different value.
You mean if we come back to this state?
Right.
Oh, okay. If there is a circle, yeah, okay. Then I understand. Okay.
Farhan, I'm looking at the two equations for SARSA and Q learning. And in both cases, we update the current policy with the learning rate that multiplies the immediate reward plus a discounted return, right? Now, I'm failing to understand the difference between the discounted return we used in SARSA and Q learning. The way I read it, in SARSA, we look at the next state, ST plus 1, and we look at the action that maximizes the return from that state, and we use that action. So basically, we look at the policy from state T plus 1 with the action that results in the maximum return in that state, right? And we use that to update the current policy. Now in Q learning, we look at the, again, right? Isn't it the same thing? We look at the action that maximizes the return.
This is actually so confusing. So let's start over here. So if you look at this, this is taking the max, but it also says that it is done in the same way as in step 2, right? And step 2 says that we are using an epsilon greedy policy. So essentially what SARSA will do is it will apply the epsilon greedy policy twice. So in the current state, it will apply epsilon greedy, which means there will be some exploration exploitation and get an action, and that will take you to S1, and then S1 again it will it will pick an action based on the same policy. So because it's epsilon greedy, so it will again epsilon greedily pick another action, which is AT plus 1, right? And then of course you just look up that value and update the table. What happens next is interesting, because if you when you try to write it down as a loop, so the loop starts at line 3 and it goes all the way to line 6, right? So what happens is that after you have executed this line, whatever value of AT plus 1 and ST plus 1 you had at this line, they are going to be used for the next iteration of the loop. So in the next iteration of the loop, you are using this action AT plus 1, which was picked from the policy that you are learning, right? If you compare this to Q learning, so first of all, the one difference is that Q learning is not using epsilon greedy policy. It is just using the pure greedy policy, which is selecting the best action, right? So it is just selecting the best action. There is no uncertainty, no probability involved. So it just uses your greedy policy. But then it doesn't actually execute that policy. So it's not going to take, because we didn't really compute any AT plus 1, right? We just found whatever AT plus 1 was, we just found the return for corresponding to that and substitute that here. So when you go back to this step, then you are going to compute AT again. And this will of course be because the iteration has progressed. So this is AT plus 1 actually. So you are again going to find AT plus 1. So which is going to be, which is very likely or somewhat likely to be different from this AT, because this one corresponded to the maximum return, and this one is coming from epsilon greedy. So it could be the maximum one, it could be something else as well.
I see. So the key difference really is that when you're looking for your discounted reward for the future state, in SARSA, you still do epsilon greedy, but in Q-learning, you do purely greedy.
Right, you do purely greedy. And of course, in this case, in SARSA, this action that you found over here, this action gets used in the loop again.
Okay.
But over here, there is no such thing.
Okay.
So if epsilon is 1, they're both the same algorithm, right?
Yes, when epsilon is same, they're both the same.
No, when epsilon is 0, they both be the same algorithm, right?
When epsilon is 0 actually, because this is greedy. This is not equiprobable. This is greedy policy. When epsilon is 0, then only one state, the state with the action with the highest return, that will have all the probability equal to 1. Everything else is 0.
And Farhan, can you explain the paragraph after the steps? The key difference is does not follow the current policy.
Yeah, the key difference from SARSA is that Q-learning does not follow the current policy to pick the second action, right? So that is what I was saying, that the action over here, that doesn't really matter, because we are not concerned with the action. We just want to find out what the highest return is. But if you look here, we are again finding AT plus 1 is, you determine AT plus 1 using the same approach that you use for AT, right? Which is applying the greedy policy, epsilon greedy policy. So it says Q-learning does not follow the current policy to pick the second action AT plus 1, which is right, because there is no AT plus 1 being computed here. That will happen at the beginning. Actually, if you write it down in terms of code, then it becomes a lot clearer, because that thing is just not written over here. But what will actually happen is, because you have computed 80 plus 1 over here, so when you go back to the starting of the loop, which is step 3, this 80 is going to be 80 plus 1, which is going to be this argmax thing from this previous step. And here it is going to be a different value.
Okay, but there's still just one global table of expected rewards and expected returns, actually, right? So current policy really refers to a specific path through that table, but it's still just one big table.
Yeah, table is, of course, there's only one single table in both algorithms. In fact, all the algorithms that we have seen so far.
Okay.
So is it that for Q learning? Sorry. Is it that for Q learning you are basically using epsilon greedy to pick the action, but you're still using greedy to update the table, whereas for SARSA you're using epsilon greedy to pick the action, and then you're using that action to update the table?
That was, I think that's right. So yes, I mean the fundamental difference is over here, right? You find an action here, and then corresponding, and now this is picked using your current policy, which in this case we can just assume it's epsilon greedy. So this action, this could be the action corresponding to the highest return. It could be something else as well with a small probability. And then you are going to use this action. So suppose we don't pick the best action, we can pick a non-optimal action, and whatever that action is, that action will get used in the next iteration of the loop, because this 80 just becomes 80 plus 1. But
So
over here,
which one works better?
okay, that is not a simple thing to answer. There is actually an article that I'm going to link to. It has some like empirical evidence and some comparison about which one should be used. In general, the key difference that sets them apart is how you are learning. So is it like you have all the data and you have generated the data and you want to learn with that, or do you also expect your algorithm to be online, so there is more data that is going to come in the future?
So just to confirm, epsilon of 1 means explore all the time, and epsilon 0 means just exploit, right? And so
Right,
in the epsilon greedy algorithm, does the epsilon decay also, is that part of the algorithm, or is that something we just added?
Right. So that part remains, whatever we did yesterday, which is decaying epsilon, because that general intuition is there that you don't want to be exploring as much as you begin to learn more. So you must
So
decay
epsilon greedy includes the epsilon decay as well?
Right. It will use
Okay.
epsilon decay. You have to decay epsilon every episode or every few episodes.
I see.
Right. So there is so much confusion about being online and offline, and specifically between SARSA and Q learning, that someone has written a very nice answer on Stack Overflow, which I'm going to share. So there are actually a few answers. I like this one because it is basically it takes the equation from the book, so our reference book, which is Sutton and Bartow. So it takes the equations exactly as they are in the book, and then it is annotating them and clearly trying to explain what the difference is. And and in the same question, if you go down a little bit, so there is another answer. There is another answer about when to use which one. So we can try to implement the first version, which is SARSA.
What should SARSA do, or any of these do, when you hit the terminal state?
That is, so you basically have to end that episode because
So you just reset, like a foosball dot reset whenever you hit terminal?
right. So these all these steps, they are sitting inside a loop which is repeating for every episode. Is anyone able to implement SARSA?
Yep.
Are you able to get a policy?
Yeah, I got a good one. It's still not optimal though, but it was able to converge in like 1,000 or 2,000.
That's very cool. I am also giving it a shot. I think I'm already almost done. Yup, with 1,000 iterations and a learning rate of 0.001, I'm also getting pretty close to an optimal policy, but not exactly an optimal one. Is everyone able to implement this thing? Did anyone else also get results which look okay, even if they are not perfect? Give it a try, please, because this is really important that we understand these algorithms, because then we are going to modify them for other use cases where for the take home project for our next week's work. And if you have if you are getting good results, maybe optimal policies with this setting, then also try to implement the second version, which is Q learning?
So I implemented the Q learning, and it was getting stuck every time I'd run it. It would it was just getting stuck every single time somewhere or another. So it was looking kind of like the greedy one initially. But I put a little bit of code in to just not start decaying epsilon for some number of iterations, and I've got an actual optimal policy out of the Q learning. But I needed to make sure it stayed fully random for like some number, and then it, because somehow when it was using the argmax, it was just getting stuck because it was the problem that Jonathan was talking about last time, where it just got stuck going back and forth between it was afraid to make a bad mistake, and it just kept hitting back on itself. But if
so how are you setting epsilon right now? Do you keep it set to 1 for, like, after a few iterations you suddenly change
so
it?
I just did it once and I haven't changed it since, but I was fooling around trying more iterations. So I'd set my episodes to 5,000 for the Q learning. It wasn't working. So then I made it so the first 1,000, I leave it at 1. So I basically just guard my decay with, like, if I is greater than an explore, and then an explores 1,000, and then I got an ideal one from it. Basically a perfect, it's a perfect policy.
With how many iterations?
It was 5,000. I haven't fooled around. It just worked, right? So I was like, oh, cool. But it was 5,000 total and 1,000 where epsilon was 1.
Okay, that is cool. I think we should be able to get convergence faster, because that was the point.
I'll try smaller numbers just to see. Yeah, in fact, I can hit optimal policy even with 1,000 episodes and 500 at 1.
Right. So what seems to be working is that you just let the policy be totally random for initial 500 steps, and then you start
then the Q learning.
Because
it needs to explore the whole space to get some initial state for the table, I think, and then Q learning seems to work well.
Right. That is fantastic. Anyone else is able to tweak something, get some results, get somewhere close? Because
in this you're missing the minimum epsilon, right? You're not checking for the
yes.
the decay.
Right. In my implementation, right?
Yeah.
Yes. Yes, thank you for the correction. So there should be a max here. Yep, even now for this run, it's a little low. What we could do is also tweak alpha a little bit. Maybe yep, at least
Shouldn't you be using the estimated returns table? The one that you said at the very beginning of the for loop?
this one, right? Okay, this one.
Yeah, that.
Yes, I
that
think
table you want to.
it's not needed, right? Because it's just an alias for the table. It's not needed because earlier we were using the temporary
I see.
variable.
Okay. Yeah.
this wouldn't affect the results, but seems like this is like optimal. Yes. Cool. So this is something that we can play with, and we need to experiment with this thing with different parameters and hyperparameters to have a good understanding of what work, what doesn't work, because there's no underlying mathematics that will tell you. Even if you read about like whether you should be using this online approach or the offline approach with Q learning, there will be conflicting information. Some sources will say that one is better over the other. Some will say that you have to try out both and then you can decide. The two are very similar. So if you're getting results with one on this small problem, the other will also have similar behavior. But give it a try. Give the other one, implement the other algorithm as well, and you should get somewhere close to this policy.
And Farhan, there is no limitation here on the episode length, right? For this, previously we were setting that limit.
There is no limitation. That is right. But this is basically because the underlying environment is episodic, so we are not running into problems. But if that is not episodic, then you have to sort of have some additional check where you just want to perhaps break out.
Yeah.
So is there something that we can use to find the accuracy or if which policy is better than the other than just looking at the returns table? I mean, I'm just trying to see if there is one number that can be used.
So yeah, so that is actually done using the v value, which we haven't looked at much. But the purpose of v value is to compare two policies, and then all the optimal policies, they will all have the same v values.
Oh. Okay.
Cool. I think we need to take a very quick look at what the project is, because now we basically have all the basics. What we will be doing in the next two sessions is basically changing the nature of this environment, making it stochastic, and those will be small changes because everywhere is because there are many possibilities for every action, so you have to account for all the possibilities. So in many places you have to take averages or expected value of a variable of a return perhaps. So like fundamentally the algorithm, the approach, everything is going to be the same. All that will change is in some cases we will be using averages, because if you are in a state and you take an action and there are multiple possible future states, then which one do you pick, or do you pick all of them? So that is sort of the only change that you need to make to most of the algorithms when you introduce stochasticity. So in the first session we will again go back to our implementation. We will change the class a little bit. We will make sure that this function over here, get next state on action, this we will introduce probability here, and then of course we'll try a bunch of algorithms and try to solve the stochastic version. We also want to do another version where things are not static, the opponents are moving around, so we will do that probably in S2, the second session of the next week. But right now with whatever we have got in our toolkit, and there is terminology, there is notation which we haven't gone through. So we'll do that perhaps today a little bit, and then in the Monday session. But we are essentially ready to take on our take-home project, which is the OpenAI Gym Taxi V3. So this is the suggested project. So the recommendation is, what I would recommend is that everyone solves this, and then if you have time and you want to aim for something more complex, then we can discuss what that other complex project could be, or if you want to bring your own project, that is also fine. But this is what everyone should be submitting. It is relatively simple. I think it is as complex as, because there is no probability involved. So this is pretty much like the foosball environment. It is a small simulated world where a taxi is picking up and dropping off passengers, and there are specific points from where you can do a pickup or where you can do a drop off, and the rules and everything, you will find them here. Right, this is the whole code for the environment, and I will encourage everyone to read through every line of this code, because this will just familiarize you with how different this is from our own implementation, right? And there will be a few differences because OpenAI Gym is based on some underlying code, right? So they have a specific types of specific classes to represent discrete action and continuous actions and stuff like that. If you look here, sorry, uh, if you look at yeah yep, if you look at this part, for example, so this will sort of make sense. This is similar to what we were doing with the states and rows and columns, but there will be a few new things as well. Render, try to understand render as well, but I'm just trying to locate the yep. Other than looking at the code for the class, this taxi environment, you should look at the discrete environment class as well, because it is using some of the features of the discrete class. So the type of state and actions, they are basically defined there. So there is a little bit of exploration that is needed, but other than that, if we just want to get started right away, so and so I just imported Gym, which imports the OpenAI Gym environment, and then it has an API right. So it has a specific way. So instead of directly having a class named taxi, it has a special way, like a factory that where you provide a string that is the name of the environment, and then it gives you back an object. So you have the taxi. Now, taxi should be an environment similar to our environment, so we can do taxi dot reset. Right, it's giving you some number. To interpret that number, you will have to go through the code, which also has all the documentation about what this number means. And taxi dot render. Right, again, this yellow rectangle is a taxi, and then these positions which are marked with different letters. These are the pickup and drop off points. These the bars that you see, they are sort of barriers. All of this is in the documentation too. And these colons, these are points where you can jump from one lane or one road or to the adjacent one. So seems to be working. You can try to look at taxi dot actions. It actually has something called action space, right? So it's not right now showing you the exact the actual actions that you can take, but it's telling you that the action space is discrete 6, and Gym has its own data types which make it easier to spin off new types of environments. So because your environment will have either discrete actions or continuous actions, and either discrete states or continuous states. So they have built a few different types of a few different classes that represent these vectors or tables to represent the state and action. So in this case, it's a discrete 6. And there are ways it has inbuilt API to sample from it. So for example, if you want to right, just run it a few times. Yep. So this returns you a random action. If you want to look at what the values are, like it returned 1 and 3. So is it between 0 and 5, or is it 1 and 6? Then refer to the documentation. It says these are the actions. 0 is move south, and then 5 is drop off passenger. So all of that is documented here. Of course, the implementation is a little different than our very minimal ones, because we have the implementation in just one cell. And this is a better, more structured, well organized library. So it's a little different, but overall in terms of APIs, things are more or less the same. So you have reset, you have step, that sorry, that is everything we need to simulate this environment. The goal is defined here. So if you want to say that you have solved this environment, yep. So the goal is to just drop off, do a successful pickup and drop off. But what we will do is we will pick up a baseline. There are different sources where people have implemented algorithms and got good results. So we'll pick up a baseline and we'll try to beat that baseline. That would mean successful drops for say 80 out of 100 iterations, whatever that baseline is. But that is what we want to do. So what I want everyone to do is sort of play around with the environment, experiment a little bit, understand how it is working. There's a little bit of encoding and decoding involved, understand that. Look at the underlying class, which was the discrete environment class upon which this is built. So understand all of that, and then if there's anything that that is confusing, that we don't understand, we will discuss that on Monday. We will define the exact requirements for the project, like I said, which baselines we have to meet, and then from Monday onwards we will have all the time to sort of work on this project. So in the classroom, of course, we'll be working on the other variant of foosball, but then the entirety of next week and the week after that you can use to implement to solve this problem. I'm hoping that this will be really easy to like solve with whatever knowledge we have right now. And if you happen to do that, and if you're looking for more, then we'll discuss another problem that is slightly more challenging. Sorry, that is slightly more challenging, and you can take a shot at that as well. For this project, I think it doesn't really make sense to make teams and work in groups. It's really simple and straightforward. But if anyone feels that they want to work in a team, then we can figure that out as well. Okay.
So this taxi V3 needs to be kind of like submitted by next Friday.
Friday. Not exactly next Friday, next to next Friday, because next Friday is when this course sort of wraps up, and then you get an additional week, like week 5, to submit the project.
Okay.
Right. And because we know about OpenAI Gym, I'm sure like most of you are already aware of it, but it's a good time to just go to the gym, the list of gym environments, which you will find here, and look at what the differences are. So we have deliberately picked something which is part of the toy text, which they have labeled as easy. Uh, but the good thing about these easy environments is also that you can render them without the need for a screen. You can just render them in Jupyter, which may not be the case for these other environments. But if because I think most of us have a system that can run Jupyter offline, so it's a good idea to look at other environments and think about which one you would aim to solve. If taxi is solved, what else you should aim to solve. And also there are other types of environments which are more complex, which we cannot solve with the algorithms that we have got right now, because these are these basically have an action space which happens to be continuous instead of discrete. But there are a few which have both variants. So for example, this one, the mountain car, and and this variant. So it has a discrete version over here and it has a continuous version over here. So it makes sense to pick this one up if you can run it. Uh, and basically why we are aiming for text environment is because if you want to debug something, if you want to print the environment, render it, then doing that with text environment is straightforward. For these environments, there is no straightforward way. You can take snapshots at specific moments, and then from there you might want to be able to extrapolate things. So it becomes a little difficult, but it's not undoable. Uh, and at the same time, if you are using your personal computer, then it's all the more easier because there are no issues with rendering. So look at these environments, because I'm sure that taxi v3 is not going to be challenging enough. And there is a little bit of history attached to these environments, because there was this paper that came out that was called Pong from Pixels. Let me see if so this is not the paper, but this is a blog, and this is something that I have shared in the references section as well. And this is a good time to really start reading this blog. Most of it should make sense. Some of it won't, like policy network, etc., because we really haven't deep dived, or we haven't even introduced neural networks yet. But I will just give you a very small hint which should make sense, and that is that so far we have been dealing with a tabular approach, right? So we are representing all the knowledge that we have about the environment in a returns table. And the issue with that is that if the more realistic the problem is, the more higher dimensional the state action space is, right? So there is a fundamental limitation to how big that table can be and how much you can learn. But what happens when you introduce deep learning is that you can replace that table, or however big that table is supposed to be, you can replace that table by a neural network which can just try to approximate the table. And that is what we are going to do in course 2. But whenever you see a neural network, you can think of replacing that neural network with a returns table, and that should make sense. But this gives you some historical perspective as well about when like deep reinforcement learning became hot again, and also a little bit of like perspective on the different approaches and what what has been done recently. This is not a very recent. I think it was published in 2016. Yeah, so it's already 5 years old. There has been a lot more progress after that, but it is one of the best resources when you're getting started. So I'll post this in Slack, but this is a good time to get started reading this blog. Did anyone try to implement Q-learning?
Yeah, so my version of SARSA gave a good policy. Q-learning was a very simple change, but the policy was not good.
Okay, so what is like totally haywire, or were you getting a decent policy but not the perfect one?
I mean, pretty much completely, like everything just points up, almost.
That is likely to be a bug.
Yeah.
That's the same thing I had. It's getting stuck. It's getting scared. Like it doesn't want to hit a bad state. If you do what I did, which was again, keep epsilon 1 for the first 500, and it'll work with that. I bet it'll fix your problem. You could try that, because I had the exact same thing. It was just they're all pointing up except for like, it kind of gets stuck and it doesn't do an exploration.
Because you are taking the facts, right?
My only change between SARSA, which I did have working, and Q-learning was in that last equation. Basically, I used the max return, just the max of the ST+1 table, instead of using my table of ST+1, AT+1. Is that the only change, or is there something else for Q-learning to get
that is the only change. Let's see. So we are finding this action over here. Yep, this one, right? And then we are overwriting this action with this one. So this is not going to happen in Q-learning. You have to make sure that you're not using this action. In fact, you won't be computing this action at all, right?
So my code looks completely different from that. Let's see.
Yeah, but the general idea is same, whether you are looking at this code or sort of this algorithm over here. So if you look at here, look at this one. So this is the online version. This is SARSA. So you compute AT+1, and then you use AT+1 in your loop in the next step. But in Q-learning, you are not computing AT+1 at all, right? So effectively AT+1 will be computed here.
So I still compute AT+1. I just don't use it when I update the table. Does that matter?
Yeah, right. In that sense, right? So basically, you're not using the previous value of AT+1. You will be doing it at the top of the loop, right? I don't know if you can share your screen for a moment.
Yeah, let me do that. Oh, it says I cannot share while someone else.
I will have to stop sharing.
Okay. So yeah, so basically I just initialized my state and my action.
Are you sharing? Yep, it's coming up.
I am. Do people see it?
Yes, I can see it now.
Right. So I have a state and an action, right, that are initialized, and then I have this while loop, right, because now I no longer have a for loop for the episodes, and then whenever I hit a terminal state, that's when I do basically the reset. I increment this I, right, because I consider that a terminal state means I got to the new episode. I decay epsilon, and then I compute AT, right? I compute my first action, which is basically the A0 for SARSA. So this is my actual loop, right? So basically I have my epsilon. I compute the ST+1 and the RT+1 and the new done by calling step for AT.
Could you show me, one second, where are you computing AT?
So AT originally was just a random from the first state, right? But what I'm going to do is I'm going to compute AT+1 here using epsilon greedy algorithm. And then I just have AT equals AT+1 and ST equals ST+1.
Okay.
You shouldn't do the ATs equal to AT+1 for for the Q learning because you want to reuse the epsilon greedy when you're doing the next step, right?
Right.
So AT has to get recalculated every time for Q learning.
All right, so this is my SARSA algorithm. So we agree about the SARSA algorithm, right? For the Q learning algorithm, I didn't follow that, right? So you do
Just
need
comment
to
out that AT, because the thing is that your new AT should be based on the epsilon greedy. So AT should always be epsilon greedy. AT plus 1 should be the like the index max or whatever. So you don't use that AT plus 1.
I don't use the AT plus 1, right? So for Q learning, right, I'm only using the ST plus 1, computing the max return and then using the max return in the update, right? AT plus 1 is never used in here.
It's right below though, right? It's
So AT gets AT plus 1, right? So I'm getting my next action from it.
you don't want to do that though. You should make an epsilon greedy decision.
It is an epsilon greedy decision, right? AT plus 1
I
here,
mean,
this is an epsilon greedy decision.
What I want to understand is, okay, no, this isn't actually. This is corresponding to 80 plus 1. Okay, this was epsilon greedy and
Right, because I'm using the action probs. The action probs was taken using epsilon greedy algorithm here.
right. It seems right because you aren't really using ATP anywhere, right? In your updates.
I'm not, right? For Q learning, I'm not. For SARSA, I am, right? For SARSA, I have AT plus 1, right? But for Q learning, I do not.
But this ATP is corresponding to the previous state, right?
The ATP one is gotten using random choice by using the probabilities. The probabilities, right, were in turn calculated using the greedy for S. Oh,
that was for S previous state.
Okay, so this should be an ST.
Yes, this should be ST. And
for SARSA as well?
For SARSA as well, right?
Yeah, okay. So maybe I should try this.
Wait. No, I think the issue was not with using ST plus 1 there.
Okay.
The issue was that
Actually, this
when
looks
you are
better.
computing.
No, it doesn't.
I think the issue is that what is happening is your action is sort of out of sync with the state because you are overwriting the action, you are storing the action here. So I think that is going to.
Okay, because what you're saying basically is that I need to do this here after I've updated for Q learning.
Yes, in fact, the last step should not be needed at all. I'm wondering how it is being used. Yes, this is, I think, closer to Q learning.
Because I should be using the updated table.
No, I think it's still not correct because you do get
Definitely much faster. No.
I will have to take a closer look up. If you can ping the entire thing on Slack, I will take a closer look.
Okay. I'll do that.
But
thanks.
But I still think that the state and actions are not in sync. Perhaps we're using a stale action.
Okay. I'll take a look and I'll send you what I had. And then there was another suggestion, right? So somebody was saying that they saw something similar, even with the correct algorithm, just with basically not decaying epsilon until what you said until you've run 500 episodes.
Right.
Yeah, I had 500 and 1,000 were the two numbers. So completely random for 500, and then n, the total n being 1,000, and I got an optimal. That's the only way I've gotten an actual optimal one. Actually.
Okay. I'll give thanks. I'll give that a shot as well on this one and see if it works for this one.
Yeah, I think actually I tried both SARSA and Q learning, and I didn't have to do any, do 500 random episodes at the random steps at the first to get the optimal. I get optimal for both. So
with just
uh,
less than iterations.
1,000 iterations.
And what about the learning rate?
Just default 0.001.
Okay. Okay, that is fantastic. But just try to run them if at least another time and just check that it's not just by luck that you got the right
Okay,
results.
sure.
Yep. So I think everyone must try the Q learning approach as well, and we will have the solutions when we meet on Monday. We'll go over that. We'll also see if there was a bug with the code, the fixed alpha approach that we were looking at, which wasn't converging. I mean, it was converging, but one of the state didn't have the right action. So I'll check that as well. But please do implement both the variants. This is sort of the starting point. There will be different variations of the same policies, and we are going to cut back on the starter code as we go ahead. So instead of having starter codes, we'll perhaps have test cases, and then you're supposed to write the code and then run the test cases to find out if it's working fine or not. But that is the whole idea for the next course. I think we have managed to finish everything we planned for today. I did want to go through terminology, but I think it would make a lot more sense if like I can share specific chapters from the same blog from where we were looking at SARSA and Q learning, and then everyone goes through that blog real quick, and then when we meet on Monday, then we like have a short presentation about every piece of terminology and notation that is being used. Does that seem okay? Okay, silence is golden. Um, okay, I'll share everything we need to do by Monday, but definitely everyone must try and implement the other variant, which is Q learning, and also try to figure out if it's not getting the right results, then what is going wrong.
Just wanted to share, Farhan, that I also did Q learning and was stuck initially. And after exploring for the first 1,000 episodes, then it gives me a good policy.
Right. So I think that I think we have two confirmation from two or three people that you have to let exploration go on for a longer time, and that also sort of brings into question the how much adjustment we are making, because we were anyway getting started with a value of 1, which meant pure exploration, but then we were bringing it down every episode. So is that really a good idea? Is one episode enough to reduce exploration? Can we do it every 10 episodes? That is also something that we need to test out.
I also want to report some findings about Q learning. So I just did not use epsilon add-on, so it's pure random, and I got the optimal in 750 iterations.
Only 750 iterations.
Yes,
Okay.
so
Yeah. So basically with 500 you are pretty close, and then with just random exploration you reach your optimal policy. But did you like try it a few times and it is working every time?
yeah, it's like I don't use epsilon at all.
Okay, that is so. So you're not using decay, right?
No.
You're setting epsilon to 1, right?
Yeah.
Cool. So yep. So there are a few things to try out. I don't have anything else to cover today. If there are questions, happy to answer them. Uh, the recording and everything, I'll update that by tomorrow morning my time when it is available. There is no real starter code for this week. It will be this notebook only. I won't post the solution, which I normally do. You will see that every time I update the master branch, I update the solution branch as well. Two reasons. One, I don't have the solution ready right now, and two, I don't want to share the solutions right now. I want everyone to figure this out and do some experimentation and have their own understanding of why things are working, why they aren't. But we will have the solutions by Monday before the session.
So for the case of taxi V3, can we kind of implement just rather than the state action table, can we implement using a neural network, that one? Or is not allowed?
You can give it a try if you think you understand how to implement that, how to replace the table with the neural network. You can do that.
Okay.
Because after all, you just need a neural network that tells you which of the 6 actions. So it has to be a neural network that outputs a number between 0 and 5. Not exactly a number. It has to output one of those numbers.
Yeah, it basically needs to output 6 numbers, and we need to do whatever the argmax and.
Right. Correct. All right.
Is there a way to create a new cell in Collab if we want to have a separate cell for SARSA and Q-learning?
Yes, of course. There are 2 ways. One, I'm not actually sharing it. 1 second. So.
Yeah, I can copy cell, but I don't see how to paste.
No, you actually don't even need to copy. So when you hover over a cell, so you see these options, right? Code and text. So you can click on code and that adds a new cell. And then you can also, I'm sure, you can go to insert and use that. And that also gives you the shortcut. So Collab basically follows these key bindings, which are typical of Emacs, which is an editor. So if you look at the key bindings, it helps if you know a few shortcuts. So generally, if you're using Jupyter offline, like this notebook, then there are a few handy shortcuts like if I'm in a cell, I can just hit enter and type something, and then I can just hit escape, and that sort of brings the focus out of the cell. And when you have pressed escape, after that, if you want to add a cell above, press A, and you see a new cell added. If I go back to this cell, and if I press B, then it adds a cell below. By default, the cell type is code, but if you want to change it to markdown, make sure you are still in this state where escape is pressed, and just press M. That changes it to markdown cell. If you want to go back to code, press Y. That brings you to code. So there are these shortcuts which are very handy if you are adding deleting cells. When you are doing the same thing with Collab, so you have to press, instead of escape, you have to press Control plus M first. So I'm in this cell, I'll hit Control plus M and then B. That will add a new code cell, or Control plus M and A, that adds a cell above it. There are also shortcuts for copy, cut and paste, which I think are just C, V, and X. So Control plus M and X will just cut a cell, C will copy, V will paste. All right. So if there are any other questions, please ping me on Slack. Yes. So I will share all the links in Slack because.
So are we able to start the taxi project right now with what we've been given?
Yes, you should be able to.
And so when it says illegal actions, does that mean you're trying to pick up or drop off in a location where there's no passengers?
Correct.
So it's not like the passenger has a choice to say, oh, I want to get picked up or anything. It's just that if you're in that location where a passenger is, then you can pick up, and that's not illegal, right?
Say that again, please.
So like if you're in a same location as where the passenger is, like you can just pick them up. It's not like you need approval of the passenger to.
No,
Okay.
Passenger doesn't have a choice.
And the terminal state is when you drop them off at the destination, or when you like drop them in a long location, right? Is it just once, or is there like multiple times that we're doing like a taxi once?
Only once. Like after you have done a pickup, then you have to take them to their desired location.
Okay. Right. Thank you.
Cool. So I'm wrapping up. Please feel free to ping me if you need anything. I'll share the resources, the SARSA and Q learning and reading and everything else in Slack.
Thanks, Farhan.
Thank you. See you on Monday. Bye-bye.